then it stabilizes. And this is due mainly to groundwater extraction. But it brings out the point, the vertical component of sea level, the vertical component of land motion has to be brought into the big picture. And we looked at this with the idea of what's the global relative sea level rise? What, the global mean relative sea level rise as opposed to the global mean sort of climate-induced sea level rise. And the red line, which has a median of about 2.5 millimeters per year, is that relative sea level rise averaged around the length of the world's coast. If you take that same data which we created globally and you average it by people, what people experience, you get the blue line. And that's 5 millimeters per year in the median. And the whole curve is pushed to the right. People tend to live in areas that sink. So again, it's not universal, but it's widespread. So this issue of thinking about substance is really quite important. And the kind of numbers we were getting with our analysis about 6 years ago was that sea levels were 3 to 4 millimeters, 3 to 4 times greater than the global climate sea level rise induced sea level rise. So that's significant. We've just got a hot off the press this week. A paper was published where we kind of repeated this analysis with much better data, and we find that the answer really stands up quite well with this improved data. So it's people tend to live in subsiding areas, and that's quite an important point to think about. In terms of the main physical impacts of relative sea level rise, you know them all, but I'll just put them up here. Things like flooding, wetland loss and erosion, salinization, something I haven't heard so much about at this meeting, but very important when you're in deltas, places like Bangladesh, they really worry about salinization. And back to this point about putting it into context, interacting factors, you can see there's climate factors that interact with these possible changes, either make them worse or offset them, and there are non-climate factors. So again, taking a sort of broad systemic approach is important if you're really going to apply this in any particular place. Looking at what this means to society, this is the kind of information, looking at trying to understand different sectors and how they're affected by these effects of sea level rise. It's a pretty dramatic across the piece, as I think you'd expect. And it was interesting, we spent a lot of time back in the IPCC being pushed by various reviewers, asked for where are the positives of sea level rise? And there really aren't any. Pretty much all the impacts, the direct impacts, are negative. We can't. There are benefits of sea level rise in economic models. Basically, big countries lose less of their land, relatively speaking, than small countries. So the Maldives loses out to the US, for example, but I think that's a bit of an artifact to my mind way of thinking. So thinking then, well, where are the kind of issues around sea level? And mentioned that this issue of working on coastal cities. So these are the cities that had more than 1 million people in 1950. And so a coastal city is a hotspot for risk. It's a hotspot for adaptation needs. It's a hotspot for coastal engineering demand. So these are places where you guys will probably know and work. If we move forward 1970, 1970, 1990, 2010, 2025, and then 2035, you can see the growth in cities that have had tremendous coastal urbanization over essentially my lifetime, and a huge concentration actually in Asia. That really stands out. So I'll mention Asia a few times in this talk, but there's a particular concentration because there's a high concentration of people. And so you can see these are the places where we have concerns. And there are those cities in the high latitudes, for example. Again, maybe not surprising, but there are parts of the world's coast where there are no cities, but they're rather cold, generally speaking. Also, particular of interest, the really big cities, the world cities, those with maybe 10 million people or more. And there's about 19 of them projected in 2035 shown here. And they're found in every continent, but again, Asia is fairly sort of dominant in the number, having more than half of the cities with more than 10 million people. So these are, again, focuses for concern about erosion. Another sort of issue to think about really is deltas. They were mentioned in the introduction. This sort of shows where are the world's deltas. The size of the circle tells you the area of the delta, and the color tells you the population density. So you can again see deltas in the Arctic, pretty light, there's no one living in there. Again, you move to Asia, there's a lot of deltas around the Himalayas. The monsoon sort of climate there, I think, also facilitates high runoff. And so you have large concentrations of people living in deltas, and also the Nile in Egypt as well, in the top of Africa on the Mediterranean. So, and these places, so the cities and the deltas, they really concentrate where people are located in the coastal zone. If we look, I mean, over time, looking globally, the data sets have got better and better. And so now we have digital elevation models where really we have very high quality data for being able to do look at people's distribution in relation to elevation, and thinking about who might be affected by flooding or whatever. And so this is using World Pop and Delta TTM, and it sort of shows you the distribution of population with about 1.1 billion people living in the low elevation coastal zone, which is that area below 10 meters elevation in 2020. So about 14% of the world's population living there. And below, you can actually see the distribution where you have a peak of population at 2 meters. So it's an interesting observation that people really do choose to live quite close to the coast, but not literally on the coast. So that's a sort of a peak in that distribution. And 75% of these people are living in East, Southeast, and South Asia. So that really, that's the place where one is saying, you're expecting to see problems from coastal hazards, sea level rise, demand for coastal engineering as well, I think. And then Africa's population, I'm not talking about projections here, but we've done frequent return here is the one, and then the high tide and the mean sea level. A widespread assumption in kind of people modeling human distribution is if people are unprotected and they live below a 1 in 1 year elevation, they move. So those are the people that don't that migrate. And so that's basically is saying, if we look at the numbers here, oops, sorry, 200 million 200 million people are living below that 1 in 1 year level, or 2.5% of the world's population today, over 100 million below high tide, and about 30-ish million, 25 million living below mean sea level. So these are people, I mean, often it's presented that these people are very vulnerable to sea level rise. I turn it around. These are people that are depending on coastal engineering to live where they live. You wouldn't have found this distribution 100 years ago. And so, you can see coastal engineering modifying where people make choices to live. And why are people living in these low locations? It's not reflecting climate-induced sea level rise yet. In the future, it will, but it primarily reflects land subsidence, what we were talking about earlier, those parts of Japan sank 5 meters. So or reclamation, as we see in the Netherlands. So those are those two processes that have kind of led to this population distribution we see today. If we think about adaptation, so we have risks from sea level rise, and how can we deal with this? Well, sea level and coast, one of the first, I think, building on the tradition of coastal engineering, were one of the first areas that really had clear ideas on how we might adapt to these challenges. And this report was produced between the US and the Netherlands in 1990 about adapting to sea level rise. And I was, just starting out on this journey. So risks are strongly influenced by adaptation. And arguably, the biggest uncertainty, people say the biggest uncertainty is sea level. Well, actually, I think it's a coupled system. The uncertainty lies between the rise of the sea and how we respond to it. It's a coupled system, and whether that adaptation is successful or a failure. I mean, if we adapt successfully, people might just stay where they are, for example. So that's really the thing that we want to understand. If we move forward to today, things haven't, we made it a little bit richer, but that we've kept the idea you can retreat, you can you can raise, accommodate, or you can protect, hard or soft. We've added the idea of advance, that's the reclamation. And one of the pictures there to the right, that island, that's Ulamali in the Maldives, which is a new island that's a meter higher than natural islands to allow for sea level rise and also tsunami risk. So it's to deal with both hazards. So you can see the advance, but so that's an addition. But I think on the right hand side there, you can see also an awful lot of the sort of warnings, the softer, what we've heard of here, the capacity to predict and forecast and warn. And I think that's useful across the piece with adaptation. And we've made such huge progress. And I think that, and where will we be in 30 years with those kinds of skills? And on the left, nature-based, which we've heard again a lot about at this meeting, and using nature as much as possible to accomplish these goals. So again, nature-based solutions are compatible with all these different approaches. If we want to think, well, I suppose going back, I mean, despite having a range of options, the issue of do we protect or do we move is often a kind of core question. So here, just an analysis that looks at, well, protection versus retreat in a kind of cost benefit a sense. And it says, where is it worthwhile protecting based on economic cost benefit analysis? And the darker a country is, the more of its coast is protected. So like China, you can see a large country, quite dark. A lot of China's coast has been protected, as you might expect. Go to the US, it's grayer, so there's less protection. Canada and Russia, they're pretty white. There's hardly any protection, but no one lives they have a huge coast and not really many people live on the coast. So if we go forward, we can see 92,000 kilometers of coast is always protected in this analysis. We're looking at, by the way, a range of scenarios, a range of discount rates, a range of views of the future population. But 90% of the world's population is protected. So people, again, the population is not uniform, it's concentrated in the cities, for example. So you can protect small lakes, you can protect most people. 65% is never protected. So, but no one really lives there either, which is why it's not protected. And then you've got this part in the middle, 22% of the world's coast, with about sort of 10% of the population is depends on the scenario you follow. So that's a more difficult decision. So I think, well, one thing I take from this, there's a large potential, a lot of coast where you'd never protect, a lot of places where you might think about nature-based approaches, although maybe not necessarily where they're most wanted because there are less people there. Maybe you want them where there are people. And turning it around protection and maybe more broadly adaptation. This is a stylized analysis. Clearly, if you can generate money to build dikes, you can generate money to do other things. So it's talking about adaptation potential. It's widely economically justifiable where there are people. But I think that really raises an important question about protection. And we tend to look at an optimization, build to some design level. What happens? The difficult question of what happens about residual risk and what happens in failure. And as sea level rises, the water gets deeper when you get failure. And I'm struck, like in New Orleans, I think it was Hurricane Betsy in '65. You saw people walking around, and they were sort of pictures. In the pictures, they were up to their knees. Katrina, they were up to their waists. Now, that's not climate change. That's the fact that New Orleans is sinking. But it makes the point as you have relative sea level rise, the consequences of failure become worse. So you have to sort of really think that through. And and I think the idea of moving maybe from risk-based to resilience thinking, clearly, I think which thinking about much more holistically is maybe an important way of developing this. When we think about decision making in sea level, there's different ways of making decisions. You can have the different columns there, exploratory analyses. You can have sort of some kind of optimization kind of cost benefit analysis that I just showed you on the last slide, you can go for robust decision making. You're building a nuclear power station. We spend quite a bit of time talking about this in the UK. You really build them rather high. You're cautious, but you can afford to spend large amounts of money. Or you can think about maybe a more flexible approach where you acknowledge that you're going to take a number of steps, and maybe you try and make those steps as short as you can. And I would think that is the way, because the deep uncertainty with sea level, which isn't going away, that's by far the best way to go, where you make a decision, you monitor it, you monitor sea level, and you learn as you go forward. The science will get better. Think what we were able to do in 30 years. I could think what we produce, how we've developed over my career, what's going to happen as we move forward. So that, I think, is the approach to take with this problem. And that's been done. Like, this is London, the Thames Barrier, so a huge piece of infrastructure, very expensive to modify. What do we do? Its design life is actually the end of 2030. Formally, it can be pushed beyond that, but that was the formal design life when it was opened, 50 years. And this picture, this cost about £15 million, the study to produce this graph, shows you the different responses that you can take um, to, and then, you can link them to different sea level scenarios, and, and then you can interpret maybe pathways through that, and and then actually monitor what's going to this. This is actually being followed for real in London. Venice, there's a this is more exploratory, but just looking at what are the choices of Venice, looking at much higher sea levels, going to 10 meters, and including abandoning Venice or retreating from Venice. And this is more of a thought experiment, but it helps you to sort of think through what are the choices here, particularly if we get the really big sea level rises. So in a way, this is more less technical than the previous figure. It's an exploratory analysis. And I think one thing I'd also stress, I think Jane McKee Smith was talking about having people that could sell things. I think one of the things we need here is vision. I mean, the Galveston Sea Wall, I suppose, is out here is a very good example. The terrible hurricane, without a vision to rebuild, this city wouldn't be here today. So I think you need a vision of where you want to go. And this is a society, that's not something that's imposed. I think it's something that needs to be discussed. What do people want? People probably don't want the world they've got anyway. They would like to develop. So how can you develop in a way that deals with sea level and deals with all the problems? So this is the Netherlands, sort of pictures of different ways with high sea level rise that the Netherlands might develop, continuing what it's been doing, or maybe different styles of protection advancing, or maybe some kind of accommodation and relocation. And maybe it's conveyed better in these sort of cartoons that kind of just capture the idea and obviously help you to engage with the public about what these choices actually involve. So I think vision is really, really an important part of the problem. So I think, implications for coastal engineering. Well, I think it's been a great conference, and wonderful to see all the things that are going on. So it's made me feel very optimistic, shall we say. But at the same time, climate-induced sea level rise is a transformative change. We are seeing a faster rise in sea level, and that's going to continue. So so you're going to have to accept, you've got to deal with that. Going to have to either move back, build higher, whatever. In coastal engineering terms, it's forever in a qualitative sense, but we don't know the magnitude. But we do know it will rise, so we know the direction of change. Addressing this has to be done, obviously, within the context of other coastal challenges and the regional local context. Clearly, everywhere is going to be different. So that problem will manifest and tackled in different ways in different places. I think adaptation involves a change in mindset with sea level. I think we've got to think bigger. We've got to think longer. I mean, particularly if you think about these multiple steps. And we've got to think more systemically about what's going on and recognize all the different drivers that are relevant to the problem. I think seeing adaptation action as a sort of an exploratory step on a journey, as rather than a solution. I mean, when I was young, it was about solving problems, and then you kind of walked away. The solution. These problems don't. They're evolving, and you're going to have to. Engineering will have to work with them and go with them. There's this need to sort of monitor and recognizing the idea of flexibility, so you can adapt to different outcomes in the future, and we'll learn as we go. So that's a change. That's a change in mindset. It's happening already. I understand that, but I'd say it's an important point to note. I think the choice between whether we protect or retreat will be kind of maybe a bit of a caricature, but it's a kind of fundamental question. And when we decide to protect, we have to acknowledge the residual risk. I find people often don't want to even acknowledge it exists. So that's I think we have to grapple that one. That's a difficult and important problem, and actually something I haven't heard at this conference. So maybe that is something for you guys to go away and think about how you deal with that. Um, I think we have our improving understanding of prognosis, prediction, and warning capability, and this is making adaptation more and more feasible. So I think as I mentioned, the developments I've seen over my career. Keep on going, guys. That's really, I mean, that capacity is excellent and really opens up potentially fundamentally new options. The working with nature approach, again, we're hearing about that. Keep going. That's very desirable for all the reasons of multiple benefits, etc. So I think the scale of the coastal engineering challenge is very large because of sea level rise. It changes how we think, but at the same time, at this conference, I'm left with optimism that we can rise to this challenge of the 21st century, and I think you've all got jobs for life. That's probably one of the big consequences of sea level rise. But I think you can also serve society in dealing with this problem in an effective way and in many new and exciting ways, taking on board these principles. The framework for thinking about it, though, I think is key. And this systemic thinking, I think, is very, very important. I've stressed it a number of times. So I leave you with that remark. Thank you very much.
Thank you so much, Robert. And I I think it's a wonderful end of the morning highlight talks as well at this conference. So there's optimism and there's lots of work to do, and you're all here to do it. So thank you for supporting all this. And I'm really hoping we can give Robert another round of applause for this talk. All right, consider this the bell. I don't have it with me, but we have 5 minutes to the tech session. So grab your stuff and find your rooms and the speakers. We also